So, hi everyone, welcome back. So today we are going to talk about network addressing and also routing protocols. So specifically for this week, we are going to discuss about how the network address translation works, as well as how the router actually views the convergence of the distance factors. That is specifically for this week. So let's discuss in detail. First one is let's discuss about network address translation and why it's important to use them. So remember that in your IP addresses, right, there are going to be several IP addresses. These are what we call the reserved range, right? Specifically, these are your blocks of private IP addresses. So then, why do we need network address translation in the first place? Suppose that you have 3 hosts that are connected to a router. Okay, so this kind of forms like a small subnet. If each of them would be uniquely identified by one IP address, then you will need 4 IP addresses. If all of them are all public IP addresses, right, then what you need to do, you need to go to IETF, buy 4 specific IP addresses to actually address these public IPs. Okay, but at some point, you might think that, oh, it's not scalable, because what happens if you have like 100 computers? Then that might be expensive, right? So what if we just have one single IP addresses, the rest of them we assign them basically private IPs. So all you need to do is to just buy one IP address for your subnet, then the rest here, they will be assigned private IP addresses. How can you do this? That is by using network address translation. Okay, so network address translation, each of these specific local hosts, okay, each of these specific hosts inside your subnet, you are going to assign them private IP addresses just for communication with your router. Okay. Now, when, for example, this point here, it sends one single datagram. When it sends outside on your router side, it will erase the private IP address, erase your port that communicates here. It will change it to the router's external IP with a specific port. Okay. So, for example, this one I assign this to port say 3000. This is 4000. This is 5000. Okay. Then when it receives this, I will change this to the router external IP 3000 and the external port 3000. It will go out. Okay. So whenever it receives, say for example, this is towards the router with port 5000, the destination port, then it knows that, oh, this is addressing to this specific thing. Okay. So the main goal is basically we want to kind of have a mapping between the private IP addresses within your subnet with the external IP address that the router has. That's essentially the goal that we have here. Okay, any questions? So 3 things that the router has to do. First one is you're going to replace every outgoing source IP and port to the router's IP and the new port number that is assigned within the mapping. Okay, then you are going to remember the mapping, obviously. Then afterwards, once any incoming datagram, destination IP and port, remove this, change it to the private IP and port to address the host within that subnet. Okay, so far any questions? No, okay.
For one private IP subnet, it can be like distributed to multiple organizations as long as the external IP address is different.
Yes, within that single subnet, right? This is, for example, this is like this NUS. Okay, NUS will have like say 0001 for example. Then say NTU can also have another 0001 as long as these two are different, the public IP are different. Okay, that's why this is called private IP. Yep.
So for this like idea, right, is it like so-called uses the idea of multiplexing in a way because all the packets now go through one channel instead of like multiple channels? Not really.
Not really multiplexing, because if I don't have this NAT, right, it still technically goes through the router also.
Oh.
It's just a way of identifying without buying another IP address. Yeah. Okay. So yeah, next we also discussed the concept about IP datagrams. I think this was before the results week, so I hope you all still remember this. But IP datagrams, they actually contain the header and also the data, right? So the IP header themselves are quite different, in the sense that when you have like say the checksum just contains the checksum of the header, if you also remember this. Okay, that's why it's called the header checksum also. So these ones can be split according to the MTU. So when you split them based on the MTU, that is what you call the this is what you call the fragmentation. Okay, so this is basically IP fragmentation. There are several headers here. Your ID, when you fragment an IP datagram, the ID will stay the same. The flag here will actually depend on if it's the last fragment. If there's no more fragments after this, like for that single datagram, then it should be flag 0. But if it has continuing data, then the flag should be 1. Okay, so basically if it's the last fragment, then flag should be 0. Offset is basically what is the first byte number. It's like the sequence number of TCP, but you divide this by 8 because it's written in multiples of 8 bytes. Okay? Any questions? No? Okay. Then now let's start the tutorial questions. So question 1, we consider the setup in the following figure. We suppose that ISP assigns router address 24.34112.235, and this is the network address of the home network. So this is kind of a private IP address. Okay, so our goal here is we want to kind of assign a specific IP address assignment for these 4 devices. How can we do that? Anyone?
DHCP.
Hmm?
DHCP.
DHCP. No. I mean, we want to kind of give them the IP address. Like we are the DHCP now. Just assign them numbers.
You just assign. You just use the DHCP.
Choose your favorite number.
Number. Wow. Okay. Okay. So maybe let's try to do this. So how many ports? How many network interfaces are there?
4.
1, 2, 3, 4. How about this? This is also an interface. Okay, so within this diagram, we actually have 5 interfaces. Your router considers as 2 interfaces. One is within your internal subnet. The other one is the one that goes external. Okay, so how about we try to assign the external side first? What is the address here?
The 24.34.112.235.
Okay, so this one will be 24.34112.235. Okay, how about these 4 others? Maybe the rest others? How about the remaining 4 network interfaces?
The router can be 192.168. It can be the network.
Yep. So yeah, basically the previous one, right? Yeah.
So 1.254
254?
can or 1.
Oh, yeah, can. Can yeah, okay. What's your name? Not from this class. You want to be taken attendance? No, okay, fine. Forget it. Sorry for those in the okay, but yeah. So you can just assign any of these. You can do what? You can do 254.138. Yeah, but this is how I'm going to do it now. Okay, any questions? Okay. So now suppose that each host has 2 ongoing TCP connections. So 2 TCP connections there, all to the port 80 of server at 128.119, yada yada yada. Provide example corresponding entries in the NAT translation table. Maybe how many entries are there, and what do you do? Okay, how many entries are there in the NAT? Benedict? 6. Why is it 6?
Because each host got 2 ongoing.
Okay. So each host has 2 ongoing connections. So this is host A, for example. This is something point 1. This is some port number, port 3000, port 3001, something like that. Then it's number 2, port 3000, 3001. Okay. How about on the... This is the local side, right? How about on the WAN side? What do you assign here?
24.34.
Okay. This will be the external IP address, right?
24.3.
How about the port numbers? Anyone else? How about the port numbers on the WAN side?
4 different ports.
4 different ports. For 6 entries? Okay, yeah. Basically you just do it. This is just 6 different ports or for 6 different entries. Okay, because you know that each of them, this is one single connection, right? So you want to kind of uniquely identify each connection there. And what's your name again? Xavier Lee. Okay. Thank you for adding the Lee. Yeah, so that is essentially.
Okay, but then two TCP connection can be from the same host, same port.
Can yeah, can.
Then
But
in that case, it's not 6.
in that case, then technically it's just not 6 years. But for this module, we assume they are not possible. Yeah. For this module. Yes.
This is the client or the host.
This one is just a normal host. Just a normal host.
So it's the client for server. The client for the server.
Not really necessary. This one is more like client to server. Yes.
Because like if there's like server, they have like welcome software or something, then you can have like different sockets on the same port. Then you can establish connections.
It is, yes. But this one is more of the client. Yeah. So it is possible, yes. But for this one, we assume that they are different. We assume they are different here. Yeah.
You can ask a question. No, for the NET, right? It works on the network layer, right?
Yes.
And how come like it's still needed to like identify the port number along with the IP address? Because at least in my logical thinking, like when it comes to network layer, it's the most important thing is just which host to send it to, then let
Exactly.
layers handle it. So I'm just wondering why there needs to be like a unique entry for each port number.
It's more like you see that in this case, right? If it is under the case of we just have like one single IP address, right? Then we can't uniquely identify how you want to address 1, 2, 3, 4, 5, 6, right? If you will not modify the port number. So this one is like kind of like one or not one we have to modify in the case of NET. Because or else if you just consider like your IP header, it only contains the IP address, right? In that case, then you can't really do much about it unless you have another IP address. You have to uniquely identify. So this is kind of the trade-off that we have to go up, change the port number. It's kind of it, yes.
Okay.
Yeah. Okay.
Sorry, then the total number of unique port numbers on the local network will actually exceed what you can represent by, like in the
Yes.
ones.
It will be the maximum number of port numbers minus whatever you reserve. That's the maximum item that you can store inside. But it's still quite big because port number is 16 bits, right? So that's 2 raised to 16 already. So it's still quite big. Okay.
6553 is 6 ports.
I don't know. You can count later. Okay. So now, question 2. Question 2 is suppose we send an IP datagram that contains 1500 bytes. We send it to a link that has an MTU of 500 bytes. So suppose that the original datagram has ID 422 and we assume that the IP header is 20 bytes. How many fragments will be generated? Anyone else?
The NAT the table, does it like update?
Does it update?
Because like within the subnet, the number of ports is much bigger than whatever that's on the NAT server. So
I
like,
think it does. I actually forgot whether they have TTL or not. I think they have TTLs. But that one I need to check again. Yeah.
because if not, like all the ports will just be occupied until
Right,
full
exactly.
days.
Exactly. I think as far as I know, every single thing on the network, they have a time to leave also, just to ensure that, okay, when it's gone, then they just update another one, right? As far as I know, I guess. Then I need to check the fine print again. Yeah. Yeah, thanks for pointing that out. Okay. So for this one, how many fragments will be generated?
I think it's 4.
You think it's 4?
Yeah.
Anyone else can give a work example? Those who haven't spoken? Off the record. I know that they already released the answers for this tutorial on Canvas. So if you all want to check for that and get a participation also, you can. But I will be asking your questions, so it's your own risk also. The tutorial is very short, they just give you the answer, right? So I will be asking your questions, so if you all want to take the risk. Yeah, because I think they released it on Thursday. They forgot their tutorials on Friday, I think. Anyone? Why is it 4 fragments? Yeah.
So the 1500 we need to minus 20 from the header.
Okay.
Then there will be 1480. So that's the amount of data, like the data length. Then for each fragment, it's 500 bytes. But then the 500 also includes the 20 bytes. We need
Okay.
to minus that as well. Then the 1480 divided by 48.
Okay. That is exactly correct. So this is your original datagram, 1500. Because it says it's an IP datagram, then your headers are also included inside. So split them again. Your pure data from the transport layer is 1480. IP is 20 bytes. Okay. So you kind of remove the IP address, IP header here. From this 1480, you are going to split them into the MTU. This one is 480, 480, 480, 60. This one is because there's another 20 bytes that you will add. So then it will accumulate to your 500 bytes MTU. So once you have this, then you attach your 20 byte IP header. Each of them will now not exceed MTU 500. Okay. So then you will need 4 fragments because data is 1480. Amount of data that you can store inside the MTU excluding the header is 480. So take the ceiling, there will be 4 fragments. Okay. Any questions on this?
And the maximum, the 480 is a multiple of 8. Let's say the MTU is a
Yes.
greater number, then you minus, then you realize it's not a multiple of 8. Then you must find the highest multiple of 8.
Kind of. Kind of. But for this module, we always give you questions that has a multiple of 8 to avoid that ambiguity. Hey, what's your name again just now?
For what?
Cheat phone. Okay. Yeah. Okay. So now what is the length of each fragment? I think this one is quite intuitive. Yeah, 560, right? Okay, MTU 500. The rest is just 40 plus 20, right? Okay. So then we now have this question. What are the values of the ID, offset, and the flag in each fragment? Now, why don't we just have a group discussion here? What if this time we start from the back, then we go one snake around to the front, each of you mentioning one item. Okay? So from the very back, fragment 1, what's the ID number? Oh, I forgot to mention. Original IP datagram, ID number is 422, being split into 4 fragments, each containing 480, 480, 480, and 40 bytes. So what is the ID number of the first fragment? Those in the back, please. No, no? No, no, next one? No, no, okay. Move forward, 1 row. Yeah. The 2 ladies behind. No idea? Idea? Okay, in front?
422.
422, okay. Beside it, the intruder.
480.
This one is 488.
The offset is 480.
For the first fragment,
Oh,
first fragment should be 0, okay? Offset should be 0. Third. Next one here. 1? 1 or 0? Why is it 1? Okay, because it's not the last fragment, right? So this should be 1, yes. See that?
422.
422 again. Offset. Why is it 60? Yeah. Okay, because you have to divide by 8, so this should be 60. Right. Okay. 1. Okay. Next. ID. Benedict. 422. Change form.
120
Why is it 120?
plus 60.
Okay.
Flex one.
Next one. Okay. Last one. Tom.
4 to 2.
4 to 2.
180
Why is it 180?
plus 60.
Yeah, like it.
Yo.
It's like 0. So.
This one? 0. Okay. Yeah. So how you do this is if you are asked for the ID number, this one is easiest. It will always follow the original datagram. Okay, they are all the same for the fragments. Then for the flag, everything is 1 except for the last fragment, this will be 0. Now the tougher side is on the offset. So on the offset, formally speaking, you have to consider what is the first byte of each fragment. So this will be 0, 480, 960, 1440. Then you divide this by 8. Okay, then it should give you this result. Okay, which is exactly the same. Any questions? So if you would like to see it in the way the lecture describes, this would be the view normally. So one IP datagram here, you fragment it out into 4 separate datagrams. But all these will contain the same ID. That is when you know that they are fragments of the same datagram. Okay, questions? Okay. Now, question 3. So question 3 is actually about the distance factor algorithm. So assume that we have this following network topology and we assume that the protocol has terminated. Each node knows the cost of the minimum cost path to every single other node. We want to fill in the following table. I understand that the table is different from the table in your tutorial. Just because I forgot to include the... I didn't forget, this was my slides from last sem. So they updated the tutorial this sem, yeah. But basically it should be from... There's a from W. But same thing we just discarded first. Okay, in my solution you will see there's a from W also. Okay, so maybe anyone can mention out the first row, maybe from Yiming. From X to W maybe. Shortest path. Shortest path. Shortest path.
X to what?
X to W. After the algorithm is converged.
3.
3, okay. Then Hertz in X to Z maybe.
5.
5, okay? So because X to Z, the shortest one is X to Y, 3, Y to Z is 2. Okay, so you actually you can do that method and you're done. Okay? Just find out from one point which one is shortest, then you fill in the table and you're done. Okay? So that is it for the tutorial, thank you, just kidding. But I'm going to show you exactly how the network actually looks into it. Okay? So I think in the lecture, the lecturer already describes also the way the distance factors are being done. So I think that's a good thing because the last few years it was not described in the lecture. But yeah, so instead of doing a more diagram method, I will actually show you this is the fine print written from the Kurose and Ross book. So this is your distance factor algorithm. On the upper side, this one is basically just initializing the whole algorithm. So for each node, you are going to create basically one single factor. Okay? Then for every single immediate neighbor, okay, for every single immediate neighbor, you are going to store the cost as part of a DRAG, okay, for your immediate neighbors. Then if it's not a neighbor, then just set it as infinity. Okay? So this one is just the initialization step. Then once you are done constructing your distance factor, so say you have 5 nodes, all of them construct their own distance factor, right? Once they are done, this will be spread together to the network, right? So that is what we call the exchanging of the local views, I think, based on the lecture. So once that is exchanged, you will go inside the loop stage. So this is just initialization, just done once. Now on the loop side, this is what happens when either you see there's a change in the link cost or when you receive a new distance factor. So when it is received, then you will run the Bellman-Ford equation. Okay, everyone understands the Bellman-Ford equation? Okay, so basically, you receive a distance factor, you will now need to update from your side what is the cost to go to each path and each node there, plus what is the assumed cost from that node to the end. Okay, that's essentially the Bellman-Ford equation here. So we are going to do this until we see that if this happens to change what is my current distance factor, if my beliefs are being changed, then I will have to share this again to everyone. That is where this will actually create more iterations. But if it doesn't change, then I just do nothing. Okay? So this will run forever. Any questions?
Is it possible you don't receive a distance vector, but then you see a link cost change?
It is possible. That is my extra question that I said. Yeah. Okay, so let's see. So suppose in this question we want to initialize this based on the formal way lah. Okay, just now in formal way just find what is the shortest path, right? So formally speaking, you will now have like say 4 different local views, or in the lecture they just simplify this into just storing your own distance vector lah. But I like to keep it as a table because it's easier to compute each of the separate Bellman forts. So local views, first step is to initialize your distance vectors. So on W's local view, W can only see x, y, and z from 3, 7, 20, right? So then this is the immediate neighbors. Update x's immediate neighbors, y's immediate neighbors, z's immediate neighbors. Okay? Everything else set is there's infinity lah. Okay? Because you haven't received any other distance vectors. So you see that this part, for example, z's local view, this row is basically my current distance vector. These other rows are basically the distance vectors that I will receive. Okay? Any questions thus far? No? Okay. Then we do the exchanging part. Woohoo, we share. Okay, so this one shares, share. Okay, this stage actually happens simultaneously. Okay, so this one is just a way of thinking it. Okay, so you share your local view. Once this is done, all of them needs update, right? Because all of them receives a new distance vector. Thus, we now run the Bell-Manford algorithm again. So for this W here, we are going to run this Bell-Manford equation. From W to W, this one is 0. Now from W to X, what you are going to do now is, what you're going to do now is from W to X, we now see there are 3 nodes, right? X, Y, and Z. Which one is shorter? For me to go directly to X, and the assumed path from X to Z, from W to X, and the assumed path from X to X, or from W to Y, and the assumed path from Y to X, or from W to Z, and the assumed path from Z to X. Okay? So, W to X, W to Y, W to Z, you can think of it like this is the factor of just the cost. This is 3, 7, 20, right? So 3, 7, 20, I can add this directly to the assumed path from X to X, assumed path from Y to X, assumed path from Z to X. Okay? So this is basically just saying 3 plus 0, 3, 7 plus 3, 10, 20 plus 6 is 36. Find the minimum, which is just 3 plus 0. Okay? So that's this one, you don't need to update it. It's still the same. Okay? Now, when you do from W to Y just now, this one assumes that it just goes directly, right? Still 7. But now, when I have the exchange views, I see that, oh, it's actually shorter from W to Y here. It's actually shorter for me to go to X first, plus the assumed distance from X to Y. Okay, it's shorter for me to go plus 3, plus 3. So then I need to update this. Okay, so this yellow part means that it's updated lah. Okay, same goes with from W to Z. I see that it's easier for me to go W plus X plus Y plus Z all the way. Okay, sorry, this one should be from W to X, X to Z. So thus, when you have this item, you see that this one is updated, right? 069. This will be shared among. Thus, everything here will still require an update again. Okay, so repeat the same thing. This one is for X's local view. Oh, I got an update here. So this one has to be shared again. On Y's local view, 6 is updated. So it has to be shared again. And finally, on Z's local view, 8 is updated, 5 is updated. So has to be shared again. That is the first iteration. Any questions? Now you see that after the first iteration, everything still needs an update. Okay, so again we update this. So on W side, I skip the methods. I'm too lazy to write. Okay, so but basically now Z is updated. Instead of 3 plus 6, now this becomes 3 plus 3 plus 2. Okay, so that's basically on the second iteration. Now this is updated to 8. Then share again, but this time this one is actually already converged on X side, right? Because this one is, yeah, if you do the Bell-Manford equation again, you will see that there's nothing changes here. So when there's nothing changes, this will not be shared anymore. Okay, so we just mark X as done. Then we go to Y, nothing change, Z, nothing change, That is when you know it converged already. So that is the entire algorithm. Any questions? No? Okay, so in this entire algorithm, the thing to notice here is once it converges, every single node, the local views are now the same. Thus, this will actually be the result. Okay, any questions?
Is there hope to get the assumed cost of x to y or y?
That one is when you exchange the local views that you send. Because at the start, right, if you remember at the this is also forget this. Yeah, if you remember at the start, before everything is exchanged, right, everything is infinity here. But once they start exchanging views, then this one you will have the assumed cost from x to y, y to y, z to y and stuff.
Cost is like what you are able to.
Yes. Yes. So after they exchange, then you know. So whenever you receive a new one, then you have to update based on what your neighbor auntie told you. Then you have to update your belief, right? Something like that. Oh yeah. Okay. Yeah. So this one is the more formal way of doing this item. You see, it spends so many steps to do this. Okay. Questions? No? Okay. Now question 4. This one is just very simple Wireshark item. So let me just go back to Wireshark. Okay. Does anyone know how to start a Wireshark packet capture? Anyone remember?
I thought just press the ring color.
Okay, so this is Wireshark here. So what we are trying to do is we want to try to observe what happens if we ping something. Okay? So how do you start Wireshark?
The shark fin icon.
Oh, you can.
Oh,
Then the right.
Let me see. Shark fin icon.
This side.
Oh, this one is for local, for LAN lah.
Yeah, I must choose the
Yeah,
interface.
but we want to choose the interface. So in that case, there are two ways. We can stop first, then we can higher. Okay, so it's either we go to capture, then we go to options, then we choose the interface, then we start. That's one way. Or another way is on your home screen, you will see these lots of interfaces, right? For example, this Wi-Fi, you can just right click and start capture. This is also possible. Okay, so is my Wi-Fi on? It's on? Okay. Yeah, so now you see that it starts capturing, right? Then now we want to try to do a ping. Okay, say for example here I want to ping google.com. So ping. Okay, now it starts to send ping messages. Yeah, so we send 4 messages there. Now when it's done, I just need to stop the capture. Then I can filter it out based on which ones are ICMP. ICMP is used for ping. So here I see that there are 4 pairs of request and reply. Okay, if I want to inspect manually, so I can go to say for example this site, then I can double click on this. Wait. Nani? Why I cannot double click? Oh, it's on my laptop. It's on my laptop. Yeah. So this is what happens here. You will see that these are like this ICMP, this is your IP, this is your Ethernet. So we go to the IP side. Now you will see that there are different things, right? So to know which protocol that it uses on the upper layer, there's this protocol side. It tells you that the upper layer actually uses ICMP. Okay, so this is how you can digest it, right? So this protocol side actually occupies just this single. I think this one is just
the bottom also there.
1 byte, yeah, 01.
The bottom also there.
Which one?
The bottom also there.
Bottom.
You can expand your packet at the bottom there, bottom left.
Bottom left.
This one, yeah. No, this one is the ICMP side, but I want to show the protocol of the
Of your
ICMP.
screen, bottom left of your entire screen.
Oh, okay, yeah. Okay, anyways, let's just use this area. Okay, so then, actually that's it. So let me just go back to the. Yes. Okay, so we go back to the presentation here. Yeah, so basically you can see the upper layer protocol from the IP header, and also you see that from one datagram to another, the checksum and identification number will be different. So ID number changes. If everything else remains the same, then checksum will be different also. Okay, because there might be certain cases where the checksum might be the same, like 2 variable changes might be the same also. So if we consider everything to be the same, except the ID changes, then definitely will be changes. Okay. So guess we still have a bit of time. So let me go through this extra question that I sent on the group. Have anyone tried? No? Okay. So suppose that we now reduce the example to a much more simple example. X, Y, and Z, 1, 2, 50. Ah, yeah. Yeah, so this one we assume that the algorithm is converged. So you now have the local views. Okay, clear, right? Now the question is, if the cost of the link between X and Y is changed to 60, how would the tables be updated?
The X and Y would immediately update.
How? So you are proposing that this will be 60 lah?
More. It'll be 2 plus 50. Yeah, they have the information, right?
So this will be directly changed to 52 in one equation.
Oh, you don't have the 50 yet.
Okay, I mean to determine what is the final table is easy, right? I think everyone can lah. How would it be updated? Or rather, if I would change, how many iterations do you need to update it? Because I think the lecture slides covers what happens when you initialize, right? But it doesn't cover what happens when something changes. Or rather, how do you even start this algorithm now with these tables that you have done?
I think like if you change them to 60 first, like both sides will change to 60.
Okay, so basically you change this 60, 60, like that lah. Then you allow it to converge afterwards.
I think so.
Make sense? Any others? This is a discussion session. Make sense? I agree with what Yongro mentioned. You can allow this to change to 60, then afterwards we allow the algorithm to converge by itself, right? Makes sense? How about the others? No one? Okay, I guess in the interest of time, let me just share this. So actually, if you think that this will be changed directly to 60, this is actually an incorrect implementation. This one works, yes, but this is not based on the algorithm that we have. Because if you see in the algorithm, right, this is exactly the fine print that we have from the book. So either when you see a link cost change or you receive a distance factor, you will still run the same exact item. Okay, it will still run this Bellman-Ford equation again. But the catch here is, you see that when there's a link cost change, it doesn't automatically change dxy. There's no part of this algorithm that says dxy equals to cxy. There's no updating there directly. So, in short, you are going to run the same Bellman-Ford algorithm with the updated cost, but the distance factor remains the same. It remains your previous old knowledge. Okay, so let's see how it goes. This one is changed to 60, right? Okay, so if this is changed to 60, then both x and y needs to get updated, right, in a sense, because you detect there's a link cost change. Okay, so x and y needs to be updated. Now, the moment where it updates is basically on this side. dxx and dzx, this one still remains the same from your previous knowledge. But now this part is going to be different. Okay, just going to be this thing is different. So when you update this, this will be 60 plus 0, instead of 1 plus 0. This one is 2 plus 3. So now it changes from 1, it becomes 5. Okay, so only this will be different. So once this is done, same goes, you exchange local views. Then this will be 52, 50, change local views. Now this side, your z now becomes, from z to x now becomes 7. Why is it 7? Because from z to x, right, what it sees now is because there's this change, but this change is not directly reflected on your dxx, dxy, right? Okay? So what happens here is, your z7, it still assumes that from z you can go to y, from y you go to z again, z goes to y, y goes to x, through that one path change. Okay? That's why when we say this y equals to 5, right? This y equals to 5 is because from y, you go to z, z is 2 point, right? Z's previous knowledge is not updated yet, it's still 3. So the path now becomes from y to x is y to z, z to y, y to x, that's why it's 5. Because it still retains the previous knowledge. Okay? Now because of this, you will see that on the next iteration, your y will now become This one is now 9. Okay? Because it will go to y to z, z to y, y to z, z to y, y to x. That is 9.
Why the y to x, right? The y go to z, go back to y, then go back to x. Because just now you say the 5 one is because
Yes.
y go to z, z go back to y, then go back to then
Because this one is kind of a ping pong. Just now when your y is updated to 5, right? Your z still assumes that your x exists. The link part of 1 exists. Y uses this. Now z uses this one again. Now the y uses that z again. So this will become just a ping pong, ping pong, ping pong back to the one course path.
It's
Yeah.
Is this the count to infinity problem? Oh, no.
Okay. Yeah. So what happens here is you will see that every iteration it will only your y by 5, by 4, by 4, by 4, by 4. It will continue this way until when it eventually reaches 52. Then you will see that, oh, it's actually faster for me from y to z to x. Boom. I don't have to go back ping pong, ping pong, ping pong. Okay? So it has to go back and forth, y to z, y to z, y to z, z to y to x. Until it reaches to a point where y decides, actually it's faster for me to y to z to x directly. So it will have to cut through that breakpoint, then it will be 52. Okay? So if you have a very large value, you will see how many iterations this is needed. And as what Yongrong mentioned, this is what you call the count to infinity problem. So this is very important because we are assuming the case where there's a link cost change. What happens if that link was dead? You will not know whether the link is dead or not. Because just go ping pong, ping pong, ping pong until it actually exceeds the amount of integer bits, then you know it's infinity. That's the problem. Okay? So, how do you mitigate this problem? Everyone understands the problem already? Understand, right? Because of previous knowledge, your algorithm is breaking basically. So how do you mitigate that case?
Just wait.
Just
Eventually you'll converge.
there's actually a smart way. Anyone knows? Maybe you can search Google ChatGPT how to handle count to infinity problem. Anyone?
Is there a hint?
The hint is you just need using 2 iterations.
2 iteration.
Okay, so let me share a bit. What if we use Yongrong's idea just now? He was saying that if I change this to 60 and allow it to converge, right? So we use a similar thing, but now what if we change it to a very, very large value that it will not go through that path? Okay, just now if I didn't change this, right, Z will still think that this is still reachable. Then it will be back and forth. What if I change this so that when there's a link cost change, tell every single one that this path is not reachable until someone discovers that it's reachable. If you get what I mean. Okay? So, this is the exact way we are doing it. What if, when you get a link cost change, I change this to infinity? I'm telling everyone that this is not possible to be reached. Until someone tells me otherwise. Okay? So I change this to infinity. I share this among everyone else. Now, when you do this thing, okay, this one's still 52. Never mind, this one's still the same thing. Now, when this 52 is shared here, Z just now from 3 it jumps to 7, I think, right?
Yeah.
So instead of jumping to 7, now you notice that at here, because your dyx is set to infinity, it will force Z to go this path directly. Instead of ping pong here, then go to x. Because this is infinity, this one will go to infinity, thus it will force Z to go this path. So it will go 50 plus 0, this will be 50. Okay, so once this is updated, share to y, now y will update based on the new knowledge. Because it now knows that, oh, from Z actually it's possible to go to x. Why don't I go from Z to x instead? So this will be 52. Now when this is done, share, converge, we are done. So this exact technique is what you call poison reverse. Why is it called poison? Because you poison the table of yx here. When you poison this out, this will share, it will immediately trigger your Z to go to x directly, instead of passing the ping pong again. Okay? Any questions? Wait, yeah?
If we can change it to infinity, then why not just change it to 60?
If in the case that it was actually, if the link was dead, this will be infinity. So it's handling a general case. But you can handle 60 also.
What
49.
Hmm?
49.
Why would you change it to 49?
Like, X, Y, Z.
If you put it 49, then yes, I think it will be X, Y, Z. Yeah. But under this case, then it will go the pinpoint direction. So right?
Why, like the Y can detect a link cost change to X, right? But it doesn't know the actual value.
It knows the actual value. The CXY is changing, but the D value is not being changed. There's a difference between the cost and the distance factor.
Oh.
Distance factor doesn't get updated, but the cost it knows is updated. Okay. Okay. So if you need a better explanation, there's actually a YouTube video on this. This one is from, I think this one is from Georgia Tech. It explains using pen and paper, so if you want to know how you do it. Okay, so bonus question. If you don't use Poisson reverse, how many iterations do you need until convergence?
Oh.
So you might want to ask me, right, Jason, why do we need to learn all this complicated way of visualizing things when all you need to do is to just point out X to Y, where is the shortest part, right? Anyone understand? The answer is because this exact thing that I discussed is a past year final question. So this was my year's final. This was my year's final. The exact question is basically these three things. If one of them changes, what happens? And yeah, the worst part is this was not covered in the lecture. So y'all can search Google on this. But I think the lecturer did cover a bit on this. So hope y'all know. Any questions? So when you are faced with questions like this, if you don't know the exact DP algorithm, that's where you get a hard time. Because if you directly change to 60 and something like that, right, then this one is wrong already because it's not based on the original algorithm. So you actually have to imagine how the views will change in every iteration when you face questions like this. Okay, if no questions, then that is it for this tutorial. So, okay, that's it. If you all haven't marked your attendance, please come forward. Edmund.
Yeah.
Okay.
Actually, can you explain again the 5 one, like how you add up to 5?
5 which one?
It's not the last problem.
Oh wait, I paused my recording, guys.
Okay.